Okay, we are back again. Once more, we are doing questions from a practice CLEP calculus exam found online. At this URL should be a proper link in the description. And we're going to pick up where we left off, which was at number 30 here. And you should note that we have seen this before. We have done this one before, but on the previous sample exam, when we encountered this one, it was in the calculators allowed section. And this time it's in the calculators not allowed section. So when we use the calculator with this, it was real easy. We just tossed the equation into the calculator, graphed it, and found the intercepts, and asked the calculator, tell us the definite integral between these 2 points, and it gave us a number, and we figured out which one of those it matched to, and it was super easy. But now if we're going to do it without the calculator, it takes a little more doing, but we are going to run through that just to show you how it is done, in case when you take the exam for real, you get one more like this in the non-calculator allowed section. Okay, so we are talking the again, the area in the region in the first quadrant. So the first quadrant is above the x-axis and to the right of the y-axis, meaning the place where the x's and the y's are positive values. And we have, I'm going to turn that square root into the 1/2 exponent right off the bat. And if you may recall, we need to know what the x-intercepts are. It was a graph that kind of looked like that. And we can tell that because the zeros are going to be x equals 0, right? If that one is 0, makes the whole thing 0. And then x equals 2, because if x equals 2, 2 squared is 4. 4 minus 4 is 0, making it a square root of 0. And anything more and anything beyond x equals 2 turns into imaginary numbers and doesn't exist. So, the square root of 0, that's the other place where y equals 0, and that's where it stops. So everything, in terms of this, there's your 0, there's your 2. So if we're thinking a definite integral, it's going to be that kind of thing. But let's see. Right, so the real trick here is this is one of those, we have to reverse engineer the chain rule, because you can see there's kind of a thing inside of another thing. So we can make a pretty accurate guess that it started out as a thing inside of another thing, and we did the chain rule to somehow arrive at that, because we need to know what it was originally in order to do our definite integral. So, but this is, looking at that, you look at that and you get dizzy. It's like, well, what the heck was that originally? Again, the chain rule, when you have an f of a g of x, a thing inside of another thing, the derivative of that is the derivative of the outside part, the f, with the original g of x inside of it, multiplied by the derivative of the g. So we have to figure out, what is our f, what is our derivative of f, what is our g, what is our derivative of g. And well, we know that the thing that's inside is the 4 minus x squared. That's a pretty safe bet. So we're going to go ahead and fill that in as our g. And the derivative of the g, what's the derivative of that? 4 goes away, so we have the negative 2 comes down. We have a negative 2. And you subtract 1. Just get x to the first. So it's just negative 2x. The real question is, what do we have for the outside? What is the original f? And what is the derivative? So we know we're ending up at exponent of 1/2. So let's start with that. X to the 1/2, that's where we're going to end up at. And so how we get here, remember when we take the derivative, we're subtracting 1 from the exponent, so it would have started with an x to the 3/2. But then when we take that derivative, the exponent moves down in front, and then you subtract 1. But we don't have the 3/2 here. We don't see it here. So that means it must have multiplied with something that just turned into 1. So we can put a 2/3 here. That way, when you bring down the 3/2, multiplies together, cancels out, you just get a 1, and you're left with the x to the 1/2 on its own. So that's looking pretty good. Let's see what happens if we assume that it's this. Let's see what happens when we do the full chain rule out on that. So we have the derivative of the f, which is that x to the 1/2, with the original inside in there, 4 minus x squared, and then multiplied by the derivative of the inside, minus 2x. So if we compare this with what we actually started with, we can see, yeah, it's pretty close. This part is the same, but the, let's see. Yeah, but we have this this minus, and we have that 2 that we want to get rid of. So what we need to bring into this is a negative 1/2, because then that cancels out and that cancels out. So we'll go back up here and we will insert a negative 1/2 to both. And you'll note that for this, that the 2 actually cancels out. So it's really, you're starting at negative 1/3 times x to the 3/2 power. And you take the derivative of that, you get that. And when you finish out the chain rule, that 1/2x and that negative 2 cancels out, and you get what we started with, what we were looking for right there. So what is our original equation? The f, the negative 1/3 times the inner part to the 3/2, with the middle in there, 4 minus x squared. And that's the thing that we want to find, the definite interval from 0 to 2. So yeah, we're not quite done yet. We now we can do the real rest of it, knowing that we're here with this. So let's just rewrite this down here. Negative 1/3 for the x to 3/2. And so that's going to be negative 1/3, 4 minus 2 squared, minus the negative, so it's a plus 4 minus 0 squared to the 3/2. Okay, so we can see pretty quickly That 2 squared equals 4. 4 minus 4 is 0. 0 to whatever power is still 0 times negative 1/3 is still 0. So all of that goes away, and we're left with this over here. And 0 squared is still 0. So we're basically left with 1/3 4 to the 3/2 power. Okay, so 4 to the 3/2 power. Remember that, well, we can split this up basically, is what I'm getting at. When you have 4 to the 3/2 power, we can say that is 4 to the 3rd power squared, or we can say that it is 4 to the 1/2 power cubed, or we could say it's 4 cubed to the 1/2 power. Either way, 3 times the 1/2 is 3/2, which when we do first, it doesn't matter. It works out the same. We could do it this way, cube the 4, and then find the square root of that. But it's far easier to say, what's the square root of 4? That's going to be 2 to the 3rd, which is going to be 8. And you get the same thing here. 4 cubed is 64. Square root of 64 is 8. So this one's just faster because you're keeping the smaller numbers. So back down here, 1/3 times 8, or 8 over 3. And if you remember the last time we did it, it was indeed 8 over 3 is what the calculator said, option B. So that's how that works, and that is a little more involved reverse engineering of a chain rule. So I had some good fun with that one. Moving on then, 32 we've seen before. 33 is going to be new to us, and this is one of those, which one must be true or which one must be false. In this case, you're asking which one must be false. So let's look at them one at a time. Well, first of all, let's think about, before we get too far into it, let's think about what this graph is telling us. This is the derivative, so this is telling us the slopes, right? We have and it does a thing at -2 and another thing at 2. So we have a positive slope that is increasing. So the slope is upwards, it's positive, and it's increasing, so it's getting steeper. And then at -2, it actually shoots up to infinity, which is not a proper function. But if we're just gonna draw it, the slope of infinity is just going straight up. And then on the other side of -2, it's coming down again. It's still a positive slope, but getting lower and lower, so it's flattening out. And then at x equals 0, you hit a 0 slope, so it's flattening out. And then it's still getting less and less and less. And then at 2, it shoots to negative infinity, so we're going straight down. And then on the other side of that, it's still a negative value, but it's getting less of a negative value, so it's kind of flattening out again. So it's something like this, where at -2 and at 2, it goes straight up vertical. So that's not a function that you can. That's why you get the asymptotes. You wouldn't be able to write an equation for this, but you can graph it that way. But you get the asymptotes. Presumably wouldn't be able to write an equation. Not sure I would know how, but we don't have to. So which statement must be false? So statement A suggests that there are no relative extrema. Well, we can see, we drew it right there, that's the maximum, and we can tell it's the maximum from the graph because we have a positive slope, slope becomes 0, and then we have a negative slope, so that is the surest sign of a relative maximum. So we know that A is false, and that is going to be our final answer. But let's just check the other 4 just to satisfy ourselves. So the function is increasing between the x values of negative infinity and 0. So the function is increasing from out here to here. And we know that's true because the first derivative of the slope is all positive. So it's going up for all of those. So B is a true statement. And the graph is concave down between negative 2 and 2. And we know that's true because that is where the slope is decreasing, right? So because the slope is positive, but it's decreasing as you move along, the slope is getting less and less. Hits 0 and goes negative, but it's still getting further negative as you go along. So that's your concave down, the decreasing slope. So that is a true statement. And then the graph of f has points of inflection at there and there. And we know that's true again. We just drew it. Concave down, the concave up, the concave down, the concave up. But we know that is true because we have the increasing slope and then it switches to a decreasing slope, and the decreasing slope and it switches to an increasing slope. And that's true even though it does it asymptotically. It's obviously still decreasing and then increasing, or increasing and then decreasing. So it's an unusual point of inflection because it's going straight vertical, but it is still a point of inflection, so that's true. And then the graph of f has vertical tangent lines, which again we said because the slope is infinite and negative infinite, those are just straight up and down, only briefly, but those are definitely vertical. The vertical tangent line meaning the slope is vertical, meaning the slope is infinite, and infinite or negative infinite, which we can see is true. So we've definitively decided that all of those are true statements except for the first one, A, which is our answer. And moving on. So 34 we have seen before. 35 we have done before. So to the next page. All right. This is remarkably an entire page of ones that we haven't done before. So let's just get into it with 36. And it's another one of these Riemann sum problems. So which of the following is a right Riemann sum approximation for the definite integral 0 to 2 of the square root of x using n subintervals of equal width? So recall when we're talking about a Riemann sum, we're talking about we are doing a approximation. Rather than doing the definite integral the normal calculus way, we're gonna pretend we don't know that yet, and we're doing a arduous way of approximating it by chopping it up into pieces. And each of these is going to be little rectangles, and then we're going to add up the sums of all these, the area of each rectangle, and then add them all together. And by saying it's a right-hand Riemann sum, we were taking the, like I drew it here. If it was a left hand, it would be more like that, where the left side of the bars is on the function, as opposed to the right-hand side of the bars being on the function. So we're going from 0 over here to 2 over here somewhere, and it's not giving us a number of rectangles. Like the way I've drawn it here, that is 6 rectangles. So the way I've drawn it, the n would be equal to 6. We have, 6 subintervals, and I just drew it freehand, so they're not equal, but it would be, if I had drawn it with the proper tools instead of freehand, those would all be of equal widths. But we're gonna, it's the answers are done in terms of n, so we have to find it for the general case, not a specific n, but just the general case. So n could be 2, n could be 50. It's however many subintervals that you're doing. And obviously, if you were calculating this by hand, the more subintervals you're doing, the more accurate your estimate is going to be, but the longer it's going to take you to calculate all those up. Of course, if you're doing it with a calculator or a spreadsheet, you can do it pretty quickly and have an n up to whatever you want. But anyway, we're getting away from the main point, which is what of these equations represents what we're looking for. And we have the sigma notation, the sum notation, which is common to all of them, so we don't have to worry about that part. But this is what this is saying, is we're going to add together all of the things for the k value from 1 to n. So where we have the k in the answers, we're going to fill in, k equals 1, k equals 2, k equals 3, k equals 4, k equals 5, all the way on up to whatever n is. And then you take all those that you calculated and add them all together. So what we're asking is which one of these represents what we would do here. So this is y equals the square root of x. And we have 0 to 2. So each one of these subdivisions is going to be, the first one is going to be 1, 2 over n, and that's going to be 2, 2 over n, and 3, 2 over n, 4, 2 over n, 5, 2 over n, all the way on up to n, 2 over n, however, again, the way I've drawn it, n equals 6, but however many n's you have, that's representing the height. Well, that's the x values. So you have to take the iterative, right? So what we have here, these are all the x values that you have to calculate to find the y values, right? So the y value, or the height, is going to be every k 2 to the n, because all your x values conform to this. You're going to add up all the different x values of 2, because you're going from 2 because the width of this that you're doing is 2, over n because you're doing n subdivisions, and then the k because that's your 1, 2, 3, 4, 5, 6, 7 that you're doing together. And you're going to add, so if you take this and you add them all together, that gives you all of the heights, all of the heights added together. But then we're still looking for an area, so we still have to divide by the width, and the width of each one of these is the 2 over n. So the sum of all the k's, 1, 2, 3, 4, 5, 6, we have the 2 over n, which is the width, and then the square root, which is just the original function, k times 2 over n, which is all the x values, and when you sum them together, they make the height, all of the heights. And so we look over here, and we have 2 over n, and written differently, but 2 times k divided by n. Because again, the 2 over n is the width, the k represents all of the steps, all of the different values that you're stepping through as you iterate from one end to the other, and the 2n is each progressive width as you're going along that you're increasing. Anyway, I hope that makes sense. There's usually only, Riemann sums is one of those things that you don't do very much of, so there's at most going to be 1 or 2 Riemann sum questions on the total exam. But yeah, basically, you think of it in terms of the picture, and think of it as the width of each bar and the x values of each value that you are going to use to find each of the y values that you were going to add together, and that gives the width, and then the width again times the 1, 2, 3, 4, 5, 6, 7, etc. inside of the original function, which is simple one this time, and then the sigma notation to show that you're taking that k through the 1, 2, 3, 4, 5, 6, etc. And that's a Riemann sum. That's how we do that one. Okay. Number 37. Let f and g be continuous functions such that the limit as x approaches -4, for whatever that is, equals 3. And the limit as x approaches -4, okay, same value there. So the limit as x approaches -4 for f is going to be 3, and the limit of the g is going to be 1. And what is the limit as x approaches -4? Again, the same thing of these things with additional math done to them. And yeah, it's a whole rigmarole and make it look more complicated, but because we've been literally given these values, we can just drop them down, plug them in. So we have the original f, which is 3, and then we're adding the g but squared, so 1 squared, which of course is just going to be 1, and then 3 times g, so 3 times 1, again that's not very exciting, minus the f squared, so we have the 3 squared, so that turns into 3 plus 1 over 3 minus 9, and that ends up being 4 over negative 6. And if we wanted to simplify that more, which they probably want, we get a negative 2/3. So we're going to write in there negative 2/3. And that is the answer. Okay. One more for this video. So we will do number 38 here. And it is the definite integral from 0 to 2 of the function x over 1 plus x. And let's see, this is another, we have to reverse engineer the chain rule here. So, now again, for an f of g of x, the derivative is f of x of the original g times the derivative of the g. And so what's our f? What's our derivative of f? What is our g? What is our derivative of g? So we are ending up with something on the bottom. So that makes us suspect that we're dealing with a natural log. Natural log of x, of the derivative of that is 1 over x. And what we have under there, the inner part, the g, seems to be 1 plus x. And the derivative of that would just be, 1. The 1 goes away, and the x becomes 1, and you're just left with the same 1. So let's see what that would give us in terms of the chain rule. So the derivative of f with the original g underneath times the derivative of g, which is just 1. So this is what we're left with. But what we wanted is this. And yeah, where do you get another x from for that? And I will admit that this one stumped me too. Maybe I didn't spend enough time trying to figure it out, but I went to a symbolic calculus program that can do such things, and I asked it, okay, what is the indefinite integral of that? And it told me, and I looked at it and said, how the heck do you get that from that? But then I worked it through. I took what it gave me, and I took the derivative of that, and sure enough, it ended up being that one. So I'll walk you through how you actually get there, but it's not the kind of thing that you're necessarily going to easily come up with. The real trick to this is you have a 1 and you're trying to get to x. You have a 1 and an x, but you also happen to have a 1 plus x. And how do you get all these things together? Well, we can kind of recognize that if we take 1 plus x and subtract, let's see, is it 1 that we have to subtract? If we subtract the 1, then we get our x. So what actually happens here? The real answer of the original is x minus natural log of x, and the derivative, well, no, that's not, the real original is x minus the natural log of 1 plus x, because when you take the derivative of this, the chain rule of this occurs just like we thought, and you end up with 1 over 1 plus x, and the derivative of the x goes to just a 1. And then you can simplify that, quote unquote simplify. You can figure you have a 1 plus x over 1 plus x minus 1 over 1 plus x, which gives you 1 plus x minus 1 over 1 plus x, which gives you x over 1 plus x. And you can, if you're more clever than I, you can kind of work into that backwards too. You can figure that, if I might have had an x there, and then you can take the 1 plus x over 1 plus x and just stick it in a subtraction there. That's unless you're a calculus professor, I don't know how you would come up with this. But anyway, let's just put that aside for now, and one way or another we've decided that this is the original function, so we're going to do that from 0 to 2. So again, we have the fill in the 2 minus log 1 plus 2 minus 0 minus log of 1 plus 0. Now we have 2 minus log of 3, and you're subtracting 0, so that goes away, and you're subtracting the log of 1. So what is the log of 1? Now remember that when you're doing a log, the log of A equals B, such that e to the power of B equals A. So what we're really asking is e to the power of what gives you 1, and the only thing that you raise to a power to get 1 is 0. E to the power of 0 equals 1. Anything to the power of 0 equals 1. So natural log of 1 is a 0, so that's another big fat 0, and all of that goes away, and you're left with 2 minus the log of 3, and that is the answer, letter B here. And you could maybe make an argument because we knew that a log was going to be involved, and because we know that it goes from the 0 to 2, we knew that we're going to get the log of 3 and the log of 0. I mean, the log of 3 and the log of 1, and the log of 1 goes to 0, so we're going to have a log of 3. So we knew that a log of 3 was going to be involved somehow, so that means it's not going to be A, and it's not going to be E. And you could maybe look at these, okay, there's going to be a 2 involved, and where is a 2 coming from? Well, you have a 0 and you have a 2, so maybe that's just another x in there, clearly. So then the question becomes, is it x minus the log of x times the log of x, or x plus the log of x? And if you work out all those options, obviously it's the x minus the log of x that is the one that actually works. But yeah, that in the amount of time on a test, you get to a question like this. This is a prime candidate for skip it and come back to it later, because this is very much not a trivial, not a straightforward you know, problem, because it's the introduction of having a addition or a subtraction actually, uh, in next to the chain rule. And then, not just having that, but the fact that then you do this fraction factoring thing, and it makes it look very mysterious. You know, when you know what it is, it's simple, but when you don't know what it is, it's like, wow, how the heck do you get from there to there? So yeah, that's the kind of one that, you know, skip it, and if you have any time left at the end, you can come back to it, and maybe based on the answers try to figure out. But that's the kind of one that, you just give up on that one and hope you get enough of the rest correct, that you don't have to worry about it. I mean, that's that's too devious of a problem, I think. That's just super unfair. But anyway, that's all the time we have for that video, and see you again in the next one.